Hello, everyone. Turn this volume down on this one. Okay. Thank you for coming to our workshop. We're going to be presenting on from raw data to research insight. And I'm Katie, and this is my colleague, Roni. Let me minimize this if I can. Okay. So before we get started, I just want to give you a little background about where we're located. So we are in Gilbreth Hall, room 308T, and if you're in person, that's just right across the hall, back in the offices. If you're online, just make your way to Gilbreth and it'll be in the offices on the third floor. So our hours are from Monday to Friday, 10 a.m. to 2 p.m., except on Tuesdays and Thursdays, we're closed from 11:45 to 1:10. So after this workshop is done, we'll go ahead and post a video on our YouTube channel. So if you miss anything or if you want to review, you can go ahead and find this recording on YouTube later. And finally, our email is scl@etsu.edu. If you have any questions, you could shoot us an email and let us know. Okay, so really quickly, here's a couple examples of how we can help you. What we do is we provide free consulting on research design, statistical analysis, and data management. There are 3 consultants, myself, Roni, and another consultant named Sechi. And between the 3 of us, we're proficient in Python, R, and SAS, and we can guide you on how to use the software. So I've got a couple of case examples down below, but I'll just tell you we do just anything about revolving around statistics. And we've worked with dual enrollment high school students all the way to PhD and faculty members. So whatever level you're in, if you need help with statistical analysis or anything of the sorts, you can just go ahead and reach out to us or come by the office. Okay, so with that, we'll go ahead and get started. Let me stop sharing for just a second so I can get it pulled up. Okay, so yesterday you should have received an email from me explaining how to go ahead and upload the Jupyter notebook that we're going to be working in. So go ahead and make your way to Google Colab and you should get this screen. So once you get to this screen, you're going to make your way over to this upload button and go ahead and click that. And then you can click on browse. And if you just downloaded the file that I sent in the email, it should just be in your downloads here. So go ahead and click on that file and open it. And it should open right up just inside of Colab. So I'm going to go ahead and move over to this screen and use the one that I had already been working on. It's the same thing. We just made like 2 minor updates and we'll mention those in the workshop. So was everyone able to, I pause it? Okay. Was everyone able to get to this point? And if not, do you have any questions? Do you need any help? Okay. Okay. In person, if you were going to follow along, were you able to get to this point? Okay, cool. All right, so we'll go ahead and get started in our notebook then. Yes.
If anyone has any issue, they can ask in the chat.
Yeah. Roni's looking at the chat while we're doing the workshop, so if you have any issues, just go ahead and put it in the chat. And also, if you're in person, just raise your hand, get my attention, and I'll stop and answer any questions you have. So let's start with part 1. So the first thing we're going to do is frame our research questions. Before we build any model, we want to know what the problem actually is. So let's suppose we have this scenario. Let's suppose we're working with a regional planning team interested in understanding housing prices in California. Maybe they have two main questions. They want to know what factors are associated with higher median house values in California, and can we predict median house values based on neighborhood characteristics? So just based on those questions that they want to know, that means we're going to be working with the outcome variable of median house values. And this is a continuous variable, so that makes it good for linear regression, which we're going to do later on when we build our model. Okay, and a couple analytical goals that we're going to meet throughout this workshop. First of all, we want to make sure we explore the patterns in the data so that we can understand them and model them correctly. Obviously, build the model. We're going to assess the model's assumptions, evaluate predictive performance, and translate results into the research insight, which was kind of the whole point. We wanted to start from nothing and go all the way to the end until we get our answers to our research questions. So let's jump right in with preparing the data. So first of all, I want to mention that we are working with the California housing data set. It's very popular, and you can, from this line of code here, the from sklearn.datasets, import fetch California housing, you can automatically load the data into this Jupyter notebook in Colab. So typically, like if you're working with your own data, you would come over here and click this files icon, and then you would click this upload button, and you would put in your data, and then you could access it that way. But since this data is already in Python, we don't have to do that. So what we're going to do in the data preparation is we're going to import the data set. We're going to expect structure, variotypes, and units, and then we'll check for missing values and obvious data quality issues. And finally, we'll identify the outcome variable and predictors we will use for modeling, which we do already know that we're going to use the median house values for our outcome variable. Something to note about these libraries here is I put them at the very top of this Jupyter notebook because they're very common. So the pandas and NumPy libraries are good for like formatting your data, and then the Seaborn and Matplotlib are really good for plotting in Python. And these are very common. Every time you're working with any type of data in Python, you're probably going to use these libraries. So I just went ahead and put them at the top. So we'll go ahead and load the data set by running this, and a quick keyboard shortcut to run this, you can click Shift Enter, and it's going to run that specific cell that you have highlighted. Okay, so we named our data set DF here, and we wanted to see the first 5 rows of our new data frame. So that's why we did df.head, and whenever you do that, it's going to print this table here with the first 5 rows from your data set. So here's our outcome variable over here on the right, median house value. And now we get to look at all of our other predictors. So we have median income, the age of the house, the average number of rooms, the average number of bedrooms, population, average number of occupants, and then finally the latitude and longitude. Okay, so next we're going to just look at df.info and df.describe. If you run that, again, you can use Shift Enter to run that quickly. This is going to give you a little bit of background information about your data. So first of all, can they see my cursor or no? You can't see my cursor. Okay, I'm going to use the pen then. Okay, so first of all, if you look right here, this output right here is from the DF info. And if you look right here, it automatically tells you how many rows you're going to have.
It doesn't show down.
Oh, it's not showing on the Zoom?
So,
Okay, I'll just highlight with my mouse then. Okay, how about that? Can they see that?
Yeah.
Okay, good. So this top table here is from printing df.info. So range index, it automatically tells you how many entries you're going to have. So this data set has 20,640 entries or rows. Data columns, we have a total of 9 columns. And then underneath that, you can go ahead and see all the columns that you have again. And this is just like a quick way, if you look at this row, the non-null count, or this column, you can see that there are no missing data from this. I'm going to show you like a cleaner way you can look at that in the next cell, but this is just a quick check. And then finally, this last column here is your data type. So it's all in float 64, which is basically all numeric. Okay, and now moving on to this bottom table, this comes from the df.describe. And basically, it just tells you a couple different summary statistics about your data. So the first thing to note here is it's a count of all of all the data in each of the columns. So if you know that you have 20,640 entries, you should see that number for every single variable if you have no missing data. So in this case, we see 20,640 for every single variable. So that is another way to check that we have no missing values. And now if you come down to mean, you can see the mean for each of your variables, standard deviation for each of your variables, and then the minimum value, your quartiles, and then finally the maximum value. Okay, moving on. This line of code here is going to just print out a cleaner version to check for missing values. So it lists all of your variables, and if there were any missing values, it would show the number right next to it, how many were missing. And in this data set, there are none, but there's a reason why I'm mentioning missing data so much, because it's important that you do something about it. Even though this specific data set doesn't have any missing values, I am just going to walk through like a couple of like which different types of missingness you can have and a couple fixes for those. So missing data can generally fall into 3 categories. First of all, you have missing completely at random. This means that the missingness is unrelated to any variable in the data set. So for example, if you think about somebody taking a survey, maybe they accidentally skipped an answer. Okay, so it's completely at random. It has nothing to do with anything. It was just an accident or an error. Okay, and then the next category would be missing at random. So this means that the missingness is related to other observed variables, but not the missing value itself. So an example of this would be income data missing more often for younger respondents. So basically, it doesn't have anything to do with the income data, but it's because the respondent is younger and income data is missing. Okay. And then finally, the third category is missing not at random. So this means that the missingness depends on the unobserved value itself. An example of this is students with very low grades choose not to report them. If you make a low grade, you're you're really not going to want to tell anybody, so you don't put it in there. So that's called missing not at random. It's on purpose. Now it's maybe it's a little bit hard to understand like the difference between missing at random and missing not at random. But if you think about it, um, the students with low grades choose not to report them, right? So it's because of that variable that it's missing not at random. But if it's missing at random, it's because of another variable that um, income data in the example is missing. Okay. So now that we addressed that, let's go ahead and talk about some common strategies for handling the missing data. First of all, the most simple thing you can do is just delete it. Forget it ever existed. It's definitely the easiest route, but sometimes that can reduce the sample size or introduce bias, and it's not always the best idea. Another more popular, I would say, route you can take is imputation. So you can replace missing values with, if it's numerical variables, you can replace it with the mean of the data or the median of the data. If it's a categorical variable, let's say just like a binary yes or no, whichever value is more frequent, you can replace the missing value with that. And then finally, there's the model-based estimates for example, regression imputation. So this one is, let me have a marker, please. No, a marker. Yeah. Okay. So model-based estimates are basically, imagine you have two variables that are highly correlated. That means they explain each other really well. So make sure everyone can see the board online. Okay, they can. So imagine, like, let's take this data set, for example. So this data set has a column called average rooms. So it's the average number of rooms, and then also a column called average bedrooms. So imagine they're highly correlated. If they're highly correlated, it's going to kind of look like a straight line. Okay? So then if, say we have missing data in average bedroom, well, since they're highly correlated, I can use this value to then predict any missing values inside of average bedrooms. And that's what I mean when I say model-based estimates or regression imputation. That's what that is. Okay. And so to pick the most appropriate method for this, it depends on two things. It first depends on the amount of missing data. So let's take this data set, for example. We have 20,600 something rows. If there was like 5 columns with missing data or something, you could just go ahead and delete it. It's not going to have a huge impact on the data. It's not going to matter that much. But imagine you have 5 columns of missing data or 5 rows with missing data in a data set that has like 40 rows. That's going to make a huge impact on the data. So you might want to consider a different method. And then also the appropriate method depends on what type of missingness you have, whether it's missing completely at random, missing at random, or missing not at random. Okay, so now that we got that out of the way, let's go ahead and move on to part 3, from exploration to modeling. So in this, we want to start with exploratory data analysis. So we'll go ahead and explore the distribution of the outcome, which was our median house value. We'll look at the relationships between predictors and the outcome. We will identify potential skewness, outliers, nonlinear patterns, or multicollinearity. Then part 3B, we'll do like a brief feature engineering section. This is definitely very optional, but it's useful. In certain cases, you may need it. So maybe not for this data set, but we did it as an example anyways. Moving on to part 3C1, we're going to do explanatory linear regression. This part's going to help us answer our first research question. So what we're going to do is we're going to fit an ordinary least squares regression model. We're going to interpret the coefficients in meaningful units. I don't know if you saw earlier, but our median house value were in one, so it was like 1, 2, 3, 4, 5. But the units are 100,000. So if you have a value 5, that means 500,000. So we'll convert those so that we can understand what's actually happening when we fit the model. We'll compare our R squared and adjusted R squared. We'll assess model assumptions using diagnostic plots and statistics. And I'll show you all that later. Finally, in this section, we're going to do the predictive evaluation. So with the same linear regression model, we're going to split the data into training and testing sets, and then evaluate generalization using root mean squared error, mean absolute error, and R squared. And then we'll compare the R squared for training and testing to see if there's any overfitting. All right, so let's go ahead and start with the exploratory data analysis. So the first thing that we look at is the distribution of our outcome variable. So two things to note. Is it skewed? Yes, it looks very skewed. It's right skewed. And another thing is, are there outliers in this plot? You can kind of tell that these higher values may be a lot of outliers just because it's just this standalone bar at the end of the plot. Okay, so moving on from the distribution, let's see. Okay, here's a box plot of the median house value. This kind of just helps to confirm that there are a lot of outliers. So typically, I wish I could show my cursor. Sometimes. Yeah. Okay. Well, typically at the top of the box plot where there's a line, if there are outliers, you can usually see a bunch of different dots. But since there are so many outliers, they're like very compacted. So it kind of just looks like a very dark line at the top. But that kind of just helps confirm that there in fact are outliers at the top end of the data. Okay. Moving on, we want to look at the correlation between our outcome variables and the other predictors. So what we did with this is ordered it from in descending. So as you can see, the most highly correlated predictor with median house value is median income. So okay, so let's look at this plot. Okay, so since it was the strongest predictor, we went ahead and did a scatter plot of it just to see what they looked like against each other. And it looks like a very strong positive relationship, which is kind of what this value up here was telling us. And then another thing to note is there's a ceiling at 5. So there's a lot of values clustered together up here at 500,000, which also validates the outliers we were seeing in the box plot and in the distribution of the median house value. Okay, so next we're just going to go ahead and look at a correlation heat map. Let me zoom out a little bit. Can't really. Okay, that's good. All right, so this shows you the correlation of all variables against each other. So what we were looking at before with these correlation numbers up here was just the correlation with this median house value. But if you come here, you have the correlation of all the variables against each other. So like what we saw earlier, this value in the bottom left corner, 0.69, is that median income is highly associated or highly correlated with median house value. But what we didn't see before was the high correlation value of average rooms and average bedrooms, which I kind of knew that because I've worked with this data set before, and that's why I brought it up for this imputation. But this, whenever you work with, make a heat map of all your variables against each other, this is a really good way to see if you're going to have multicollinearity. And if you don't know what that is, that's basically just whenever you have two predictors, not your outcome variable, but two predictors that are highly correlated with each other. And whenever you're going to go fit a multiple linear regression model like we are, that can cause issues. All right, and then so we're going to move on to the feature engineering, and I'll pass that off to Roni.
So as Kerry said, that feature engineering is optional, but sometimes it can show a lot of things about the data. Sometimes the raw data doesn't have the enough useful info or enough useful information. So you can make new feature from the existing feature to say more about your data. So, for example, in our case, we have average rooms and average occupant. So if we divide this, we find the the rooms per occupant. So that actually means like if we take one person, how many room they have. So this variable didn't exist in our raw dataset, but we made it so that we can do prediction using that model. So sometimes when you have data sets and it had to say, okay, what's going on in here? But with feature engineering, you can make a feature that's more telling to your research question. So that's what we did here. So feature in short, feature engineering means that you are creating a new feature or a new predictor for your needs. So Katie is gonna do the rest of the regression.
Okay, so before I move on, let me just say something real quick. This is supposed to say rooms per occupant. I updated it, but I think that I loaded the wrong the wrong notebook. So let me just go over here and try to get on the right notebook. Pretty sure this was the notebook I was supposed to be on.
If you go down there, I made that change.
It also says rooms per household. Sorry, let me just check and make sure I'm on the right version. This is the change that you made, right?
Yes.
Well, yeah, okay. Well, I guess I don't know what happened to that. I guess it just got left out.
Oh yeah, so can we make the change?
I can change it now. Okay.
Oh, sorry. Yeah.
Yeah, so this is supposed to be rooms per occupant. Little typo. Okay. But anyways, moving on. So the next thing we're going to do is fit a linear regression model. So the goal for a linear regression model is to understand the relationship between a continuous outcome and one or more predictors. So we do have a continuous outcome because if you remember, our median house value is continuous, and we have 8, let me see, well, now 9 other predictors since we made the rooms per occupant feature. So this is the formula that we use in linear regression. It's if you're working with simple linear regression, that means that you're using one variable to predict one outcome. So that formula would be the same thing as what you learned in high school algebra. It's like y equals mx plus b. It's just a slope, and you're trying to fit a line to your data. But since we're doing multiple linear regression, it's y equals beta naught plus beta 1 x1 plus beta 2 x2 plus all the way to beta 9 x9 plus epsilon, which is the error term. So each of the coefficients, which are these betas, they're called the coefficients, represent the expected change in the outcome associated with 1 unit increase in the predictor holding all other variables constant. That is kind of a mouthful, but I'll explain in the interpretation later so that you can see it. So we're going to go ahead and fit an ordinary least squares regression model. And let me just explain what ordinary least squares is, like really quick. Is there an eraser in here? No? Okay, I have more board space. Okay. So whenever you want to fit linear regression, it's going to look similar to that graph, honestly. Let's just say y, x. Okay. So say that your data is like this, like it's trending upward. It's trending in a linear upward direction. So now you want to fit this line through here the best possible, the most optimal way that you can. And the way that you do this is by doing ordinary least squares. So what ordinary least squares does is it calculates the distance each of these points have to the line. Okay? I'm not going to do all of them, but just imagine all of these, it's going to calculate the distance from the point to your regression line. And the idea is the best fit that it's going to give you is when the distance between these points and the line is the smallest. So that's exactly what we're going to do in this code. So first of all, we're going to import stats models as SM. That's just a package that we use to be able to do linear regression in Python. And then we want to set y as our outcome variable from the data frame. So we do that, and then the x is everything in the data frame except for our outcome variable, median house value. And then this is just, let's see, let me highlight it. This line here is just something that's specific for this package, because whenever you are fitting a linear regression model, you have to have this intercept value, this constant, and this package just doesn't add it for some reason, so you have to add it manually. So that's just what this x equals sm.addConstant means. And then finally, this line here is going to fit our model. And then we print the model summary. Okay, so there's a lot of things to look at here, but we're only going to discuss the important ones. So I'm just going to go ahead and scroll down here. To evaluate the overall fit, we want to look at the R squared and the adjusted R squared values. So for simple linear regression, it's okay to look at, and you should look at R squared if you're doing multiple linear regression like we are. You want to look at the adjusted R squared because it penalizes for,
More variable.
yeah, more variables. Thank you. Okay, so this model explains about 64.7% of the variability in median house value. And then our F statistic tells us that, well, the F statistic p-value is low. So that tells us that the predictors as a group are strongly associated with the house value. And so if we go back up to our table, that's where I got these numbers from. So our adjusted R squared and R squared is 64.7%. The F statistic, I should probably zoom in a little bit. Let me zoom in. These numbers are small. Okay. So yeah, that's where I got these numbers from. R squared, adjusted R squared, and then here's our F statistic, and this is our p-value. And since our p-value is low, practically zero, that tells us that the predictors as a group are strongly associated with the median house value. Okay, so let's go into interpreting the coefficients. I'm not going to do all of them since we have 9, but I'm going to talk about these. Let's see. Oh yeah, so remember that the median house value is measured in hundreds of thousands. So if you want to convert it to dollars, you have to multiply 100,000 by 100,000 for all of them. So the two largest coefficients were the median income and the feature that we engineered, the rooms per occupant. So if you go back up here in our table, here is the value that we're working with. And then for median income, and then here is the one for rooms per occupant. So all I did was grab those out of that table and then come down here. So to interpret this coefficient, think of it like this. If you hold all other variables constant, a 1 unit increase in median income is associated with about a $41,100 higher median house value. So as median income increases 1 unit, then the median house value is going to increase by about $41,100. Okay, and then for rooms per occupant, as rooms per occupant increase by 1 unit, it's going to have about a $48,200 higher median house value. Okay. And then, yeah, latitude and longitude had very strong negative effects. So these two values here. Does anyone guess why this might have an effect on our outcome? The latitude and the longitude of California. What does that matter? Does anyone know?
Yes.
Does not matter. Okay, it does matter. What were you gonna say, Sam?
Oh, I mean, is this houses, right?
Yeah,
It's about houses. So, I mean, houses, price depends on where it is located.
yeah, location is really important. If you think about, yeah, home prices are different based on location, yes. But if you think about latitude and longitude specifically, your longitude is your east to west, okay? So the more west you get, the closer you're getting to the west coast of California. Nobody wants to live on the inland of California. Everybody wants to be on the beach. So as you get more west, your prices are going to increase. So therefore, as longitude gets larger, median house value is going to decrease, and vice versa. Okay. And then for latitude, it's kind of the same thing. So as latitude increases, median house value decreases. Okay, I had to think about it. But think of it, it's think of California again. So like you don't really have your big cities in the northern part of California. You have San Francisco, Los Angeles, and everything as you're going south. So that's why those are so strongly correlated or strong predictors for median house value. Okay. And then finally, the condition number is very large, and all that tells us is that we have multicollinearity, and we know that because average number of rooms is very correlated with average number of bedrooms and average number of occupants, and then latitude and longitude, of course, are correlated. Okay, moving on. So, like I said earlier, whenever you're doing simple linear regression, you want to look at your R squared. If you're doing multiple linear regression, you'll look at the adjusted R squared because it penalizes for more variables. In this example, the adjusted R squared and just the regular R squared ended up being the same value. It's probably not exactly the same, but it was rounded to 3 digits. So if you were to expand, they'd probably be a little bit different. But with a very large sample, in this data set, we have 20,640 rows and 9 predictors. The complexity penalty in adjusted R squared is tiny, so adjusted R squared ends up very similar to R squared and almost equal. Okay. Moving on, let's talk about our assumptions. So we have a bunch of different assumptions that we need to meet whenever we perform linear regression. The first one being linearity. And that's just like you want your predictors and you want the relationship between your predictors and your outcome to be approximately linear. And then next, you would like to have independence, and that means you want your residuals to be independent of each other. The third assumption, this word always gets me, homoscedasticity.
Homoscedasticity.
What did he say? Okay. This just means that residuals have constant variance across all x. Another assumption, you want your residuals to follow a normal distribution. And finally, you don't want any multicollinearity. This is only an assumption for multiple linear regression, by the way, because if you're only working with one predictor, it's impossible to have multicollinearity between your predictors. So that's why this is only an assumption for multiple linear regression. So I'm not going to go too deeply into these. I just wanted to mention them because it's a good place to start, just to be able to know. But I'm going to just talk briefly about a couple of different diagnostics, like ways you can tell if your model has met these issues or not. So we'll go ahead and run this huge code block. Zoom out a little. Okay. So for linearity and homoscedasticity, we can plot the residuals against the fitted values. And that is what this plot is here. Let me zoom out just. Okay. So what you're looking for in this plot is you would really like to have a random scatter and no pattern. So this is kind of an example of what you don't want. This is bad. Good for teaching. But this possibly violates the linearity assumption, and it definitely violates the homoscedasticity assumption. Okay, and so the next plot Okay, so next we want to check the normality of residuals. So to do that, we're going to look at the distribution and then also look at a QQ plot. So it's hard to see. Okay, so this is the distribution of our residuals. So it's not skewed. It's centered around 0, but it's a very high positive kurtosis. So that means it's very kind of clumped up into the center, and it should be spread out more evenly. And then if you look at the QQ plot, this should be these points should follow roughly a straight line. So it does in the center, but these two ends tell us, number one, that we probably have outliers, and number two, that maybe we have some kurtosis, which we definitely do. Okay. Next, I did the Durbin-Watson test and multicollinearity check. So something to note about the Durbin-Watson test, this statistic did come like out of the summary table from the model earlier, but I just put it here. So I made a little note here. The Durbin-Watson statistic checks for autocorrelation in residuals. It is most relevant in time series settings, which this is not time series data, but we examine it here as a general diagnostic for potential dependence. And usually you want a value between like 1.5 and 2.5. So I wouldn't take this too much to heart. Okay, looking at the multicollinearity check, you want to calculate this metric called the variance inflation factor. And usually, if there's no multicollinearity, you want to see a value around 10 or less. So we kind of knew that we had multicollinearity. We saw that by looking at our heat map. Latitude and longitude definitely correlated. Average rooms, average bedrooms, rooms per occupant, definitely all of these variables we kind of thought, yeah, they're definitely multicollineated. And then the rest of our variables are fine. Okay. And with that, I'll pass it on to Roni.
Okay, so far we did explanatory modeling, but if we want to do prediction to, let's say, that data set is from, let's say, until 2010. If we want to do it like, let's say, on data on 2015, then we need a different approach for our modeling. Because if we just model our data, if we model that only on our data that we already have, then our model is going to learn patterns from that model. So it's not going to do well if we put the model on unseen data. So to see how good our model is on unseen data, we do the cross-validation. Okay. So for example, in this, so first of all, from scikit-learn, we import the train test split. So what it does, it split the data, split our data into two halves. So for, let's say, for 80%, we're gonna train our model, and on the 20%, we're gonna test our model. So we are never gonna use that 20% in our modeling, so that the model can't learn the pattern from the data. That makes sense? So this train test split, So we put our X, our predictor variable, and our this
Outcome.
outcome. So our predictor variable and outcome variable, and this is the test size 0.02. It says that our test size is gonna be 20%. So you can change it according to your liking. So you can put 0.03, then it's gonna be 30% on test size and 70% on the train side. So this random state is just for the reproducibility. So if you run the same program, you're gonna get the same. But if you didn't put 42, then every time is gonna be different. Okay. So similarly before, we train our model. This is our model on our train data and our Y train and X train. Okay, this is our predictor and this is our outcome. So now we're just using this train and this X train and Y train for the modeling. And we're not doing anything with the test set. Okay. So in this line, we use the same model to predict our X test dataset. So this dataset is the model never seen this dataset. So we are just predicting based on that dataset. So if the prediction is similar, so that we can see, okay, our model is generalized well. So if we give them new data, it's going to do the prediction better. But if we see our prediction and our model prediction on train is really good, but on the test sets it's really worse, then it says that our model just learned a pattern and it doesn't know anything about the data. So here, that's what it did. So we just made the prediction based on the test set, and this is just for the later. Now we're gonna do some metrics, and from the same scikit-learn matrix, we imported mean squared error, mean squared absolute error, and R-squared error. So R-squared score. So we're gonna find this mean squared error from our test set and our predictions. Okay. Similarly, for this one, mean absolute error. Also, RMSE is just the square root of MSE. Okay, this is mean squared error. So here, this is gonna be important later, that the square, it's always square our error. So if we have like 2, it's gonna be 4. If we have like 5, it's gonna be 25. Okay. So here, we are just gonna print our RMSE, root mean square error, mean absolute error, and our R-square score. So we see that our RMSE is 0.687, our mean absolute error is 496. As Kelly said, okay, so first, let's say, look at the root mean square error. So as I said earlier, that it always square our error. So if you have error that is outlier, like really big or really small, it's going to square it. So it's going to have like more influence in our prediction. Okay, so that's what it says. The measure the average prediction error, giving larger weight to bigger errors. Okay, and here we have mean absolute error, and here we have R-square. So we're going to talk about this with our example. So here we see that our root mean square error is 0.687. So this corresponds to that our average prediction error is $68,000 because it's 0.687. So we multiply it by 100,000. Okay. And because RMC penalizes larger error more heavily, it reflects how well the model handles high value homes. Okay. So if most of the houses are like 500,000, is one house is like 10 million, then it's gonna punish the model more if you use RMSE square, okay, error. And mean absolute error is 0.496. And this just the error what you have. Let's say our model thinks the house price is $200,000 and the actual is like $150,000. So this always means like the error is plus or minus 51,000. Mean absolute error. So it just makes the absolute means it's like negative plus or minus. Okay. And the R square, this is important because this explains that how much variance that our model explain. Like all the data we have, how much this data explain the housing price. Okay, so here we found that it's 0.64. So that means that all the data we have and our model approximately explains 64% of the variance or variability. That means that other 26% is don't depend on this data set. Okay, because it could be like trained to buy a house somewhere. It could be like, during winter the houses price is different from different places. So our all the data we have just can, and this model, using this model, can explain our 64% of the variable variance. So if you use different model, that model can explain maybe more or maybe less. Okay, so here we see our R square on the train set and our test set. Okay, so the training R square is 0.649 and our testing is 0.640. So this means the model we have, or the ordinary least square model we have, generalize well to our data. Okay, let's say if it was, the testing was 0.6.5, then there's a big difference. Okay, that means the outlier influencing our model or is overfitting our model. Okay. Okay. Here it says, that's what I said, that if training R square is much higher than a testing R square, then it's a sign of overfitting. Okay, if they're similar, that means it's good, and our model generalize the housing price well. Now we go to part 4. And so after you've done all this, you have to say what you did. If you have a client, or if you have like professor, you have to explain. So these are like, as we said, a good analysis is not complete until the results are translated into clear and defensible conclusion. So it's not enough just to do all this calculation if you can't explain it well. So in this section, we'll do our answer our research question and communicate our effect size and acknowledge our limitation. So this was our first research question, that what factors are most strongly associated with the median house value in California. So the evidence shows the OLS model, the model we did, explain the R square is 0.64, meaning that included prediction and collectively capture many of the major drivers of the price difference across neighborhood. So that means that our model explains 64% of the variance of the housing price in California. And if you look at the coefficient, So with the median income house, the median income is the strongest predictor of the housing price. So if everything stays the same, if for one unit increase in median income, the housing price increase 0.411 or $41,000. So if everything has to be same, I'm going to say that again. If everything stays the same and per one unit increase in median income, the household price is going to increase $41,000. Okay. We can do the same thing for room per occupants. If everything stays the same on average, if the unit of rooms per occupant increase or change one unit, the housing price is gonna change $48,000. I hope it makes sense. So we also see from our model, we can see the geographic location, the latitude and longitude as a strong say in our model or in our housing data. What we conclude for our research question 1, that higher income areas and areas with more space per person tend to have higher median house values. Okay, and the location capture a substantial regional price difference across California. Also, important caveat that we also have to consider that our model wasn't perfect. It only explained 64% variance. Also, there are multi-collinearity. So our model is like, since it's a linear regression model and it has multi-collinearity, so it might not be the best. Okay, so several predictors are correlated. So we should be cautious about overinterpreting the exact size of individual housing structure variable. Okay. And if you go to research question 2, that how can we predict using our model? So evidence shows that using the train test split, that our model still achieve 0.64 R square, 64%. So it has the same explaining power in housing price. And when it comes to RMC, it's 0.687, and it's also closely matched to our original least square method, or our original model. So and it's the same goes for mean absolute error. So, and basically, in short, if before doing the train test split and after doing the train test split, this metrics are similar, then your model is going to be good on prediction. If they differ a lot, then that means your model is not going to do good on prediction. Okay, so we always want to see after train test split that these values, these metrics are similar. Okay, so what's the conclusion? Yes, a linear regression model using this neighborhood feature provides reasonably strong predictor performance. However, even with a solid R-square, prediction error still can be order of 50 to 70K, which is important. So when you are trying to explain this to shareholder or anyone in interest, you have to say that, okay, so this is our model, but even if our model is doing good, but still the error can be 50 or 70K. So this thing always depends on your data set, on your questions, because maybe in Johnson City, they have you can buy a house with 70K. Okay, but for California, it's not be too much. So it depends on the location or depends on the variable you have. So you always have to explain, okay, this is our model, this is our prediction, and but still we have this much error. Okay, so that concludes. So our final takeaway that median income and space per person, a room per person are the strongest signal in both explanation and prediction, and geography or location matters. The model is useful for insight and approximate prediction, but it's not perfect. If the goal is to improve prediction, the next step we could use a nonlinear model, a quadratic model, or a random forest model, or some other model. And that's conclude our workshop. And if you guys have any question or concern, let us know.
Stay for just a second. Since we are the statistical consulting lab, we put together a survey for you guys to let us know how we did. So please, let me share that. Please, if you have the time, it only takes like 1 minute. It's like just a couple of multiple choice questions. Just let us know how we did. And if you have any questions, we're gonna stick around for a few minutes. So just let us know. Otherwise, you're good to go. Thank you.
Thank you for coming.